In the final days of November 1918, a Royal Navy cruiser moored in Copenhagen to refuel before entering the Baltic. The exact fuel state is uncertain in the surviving public record, but later Estonian environmental reporting worked from an upper estimate of up to 780 tons of heavy fuel oil still associated with the wreck. This thick, viscous petroleum was heavy and difficult to manage, requiring heated piping systems just to flow through transfer valves. What began as routine logistics became the hidden legacy of the vessel. The fuel was meant to give the warship long-range endurance on the open ocean, but instead it became a permanent, toxic payload hidden below the waterline. The warship was HMS Cassandra. She was a fast, heavily armed, C-class light cruiser, measuring about 450 feet in length. Designed with a narrow beam and displacing a little over 4,000 tons, the vessel was engineered for rapid transit and prolonged naval engagements in hostile waters. Although the November armistice had officially halted the primary global conflict, Cassandra sailed directly into a highly volatile secondary combat zone. In early December 1918, the cruiser joined a British naval squadron transiting the freezing Baltic Sea to support Estonian forces against Bolshevik advances. The mission required deep penetration into a maritime theater still heavily saturated with lethal, unrecorded remnants from the Great War. On December 5, 1918, the squadron was on passage to Tallinn, moving through the Baltic near the Estonian island of Saaremaa. The dark surface visibility offered absolutely no warning of the threats tethered just below the waves. The seabed concealed an uncharted German naval minefield, a dormant defensive line left over from earlier regional deployments. Cassandra struck a submerged contact mine while moving at standard operational speed. The explosive payload detonated with devastating force directly against her forward structure. The massive hydrodynamic shockwave tore open the outer hull, causing catastrophic and immediate flooding across the forward watertight compartments. Flooding spread quickly through the damaged compartments, and the cruiser sank fast. 11 crew members died as the 4,100-ton vessel disappeared into the dark Baltic. When a warship carrying bunker fuel sinks with violent bow damage, tanks and compartments located away from the immediate blast zone do not necessarily rupture at once. They can descend with the hull, still enclosed by internal plating, frames, and bulkheads. This begins the mechanics of a long-term environmental threat. The ship becomes a sealed containment vessel on the seafloor, holding heavy oil in freezing depths behind a thinning barrier of maritime steel. Saltwater corrosion slowly oxidizes the plating, preserving the outer geometry for decades while steadily weakening the containment envelope. For nearly a century, the exact resting location of the warship remained a total mystery. Shifting sea states and chaotic wartime navigation records left her final coordinates completely unresolved, though maritime historians ultimately fixed the general sinking zone off the coast of Estonia. Beyond the physical loss of the ship, the disaster created a strict legal and ethical boundary. Because 11 British sailors died in the sinking, the site must be treated with the care owed to a military loss site. But the legal protection does not arise automatically from the casualty count alone. As a Crown warship, HMS Cassandra remains a sovereign immune vessel unless the flag state expressly relinquishes that status. Any survey, sampling, salvage, or fuel recovery would require proper authorization, coordination with the United Kingdom and Estonian authorities, and strict respect for human remains and underwater cultural heritage. The 450-foot wreck settled hard into the freezing seabed, establishing a silent, deteriorating footprint on the Baltic floor. About 315 feet below the surface of the Baltic Sea, a crushing column of cold water isolates the wreckage. At roughly 100 meters, the ambient pressure operates as a continuous, unforgiving physical barrier. This environment makes diver-led work difficult and pushes any responsible operation toward remote survey, careful planning, and controlled engineering limits. The depth and cold define the first layer of risk governing the submerged site. The Baltic environment adds a deceptive preservation effect. Freezing temperatures, unusual salinity profiles, and low oxygen levels slow the visible decay of century-old maritime steel, allowing the wreck's overall geometry to survive far longer than it might in warmer, oxygen-rich water. But preservation is not stability. The cold delays collapse while the steel continues to lose strength, leaving a hull that can appear intact while its load-bearing capacity steadily declines. Beyond the threat of a deteriorating hull, the wreck may also carry secondary hazards that restrict operational access. Historical descriptions of some wartime paravanes show that certain models use mercury oscillators as part of their depth control system. But the surviving public record does not confirm that HMS Cassandra carried mercury-filled paravanes at the moment she sank, or that those components remain exposed on the wreck today. The safer engineering assumption is not certainty, but caution. Any intrusive work would first need a hazardous materials assessment before teams treated the weather decks or scattered fittings as safe. Together, the depth, hazardous material uncertainty, and degrading steel mean Cassandra cannot be approached like a shallow water salvage job. In shallower coastal waters, commercial diving teams can sometimes use hot tap pumping, landing equipment on the wreck, drilling through hull plating, installing extraction valves, and pumping trapped oil to the surface. At roughly 100 meters, any hot tapping operation would become complex, expensive, and highly dependent on remote survey data, diver safety limits, and hull condition. Before any valve could be installed, engineers would first have to prove that the local plating still had enough thickness, strength, and surface continuity to hold a seal. If the survey showed severe thinning, uneven corrosion, or local cracking, a forced tap could become more dangerous than the leak it was meant to control. The hydrodynamic forces, heavy salvage rigging, and aggressive cutting friction generated by attempting to penetrate the bunkers could easily trigger a localized structural collapse. The brittle structural plating would likely shatter under the immense localized stress of an industrial drill. Instead of safely extracting the trapped pollutants, a forced physical intrusion could instantly rip open the fragile containment envelope. This catastrophic failure would dump the entire payload directly into the water column. The site is locked in a severe operational bind, defended by the very environment that is slowly destroying it. If direct physical intervention is too dangerous, engineers must find a way to measure the threat without touching the hull. Mapping a massive, highly degraded steel wreck lying deep in the total darkness of the ocean floor requires entirely abandoning optical visibility and relying exclusively on high-frequency sound. Optical cameras provide only a narrow, localized field of view, making it impossible to capture the overarching geometry of a 450-foot warship in a single image. To comprehend the full scale of the site, the investigation must shift entirely to acoustic energy. In the year 2010, the Estonian Navy minehunter Ugandi deployed advanced acoustic arrays into the freezing waters to definitively locate the precise coordinates of the submerged cruiser. This initial discovery pinpointed the exact location where the vessel struck the seabed. However, locating the wreck was only the first necessary step in a much larger engineering challenge. With direct contact ruled out at this stage, marine engineers turned to acoustic blueprinting, a non-intrusive survey method built from high-frequency sound rather than physical touch. A surface survey vessel drives precise, predetermined track lines back and forth over the target area. As the ship maneuvers, a hull-mounted multi-beam sonar transducer emits a wide, sweeping fan of high-frequency acoustic pulses down through the heavy water column. Hundreds of thousands of individual sound waves travel through the freezing Baltic currents every single second. When these pulses strike the flat seabed or the jagged, unnatural geometry of the sunken warship, they reflect back up toward the surface. Highly sensitive hydrophones capture these returning echoes with extreme precision. The survey computers calculate the tiny interval it takes for each acoustic pulse to leave the ship, hit the wreckage, and return. But the speed of sound through seawater is not a fixed constant. It changes with temperature, salinity, and pressure, so survey teams measure or model the sound speed profile through the water column before converting echoes into distance. By processing millions of these timed echoes, the system builds a dense, high-resolution, three-dimensional model of the wreck's exterior. Acoustic blueprinting forms the technical foundation of the non-intrusive survey protocol. In the year 2021, the Royal Navy Hydrographic Survey vessel ECHO arrived at the coordinates to execute this process, running disciplined multi-beam passes across the site. The resulting model confirmed the main hull's resting geometry, captured large-scale deformation, the overall angle of the wreck, and the layout of the surviving armor belts, establishing the external baseline for future environmental monitoring. Despite that gain, multi-beam sonar has a hard, proof ceiling. Its pulses reflect off solid maritime steel rather than penetrate it. The survey can define the exterior shell, but it cannot show the liquid contents inside, the condition of buried holding tanks, whether oil has migrated through failing bulkheads, or the distribution of pollutants across internal void spaces without physical drilling. A small, slow, drop-by-drop release of heavy fuel oil has been observed escaping from the deteriorating steel. This gradual leak establishes a critical warning signal for the entire baseline investigation. It forces a fundamental shift from analyzing the overarching outer boundary of the wreck to confronting the physical reality of the toxic payload trapped inside. The massive structure of the cruiser is not perfectly sealed. Visual evidence from recent wreck footage penetrated the darkness and documented the slow leak. The cameras recorded small, dark traces of fuel escaping from the wreck before rising and dispersing near the surface. The main body of the warship lies on its starboard side upon the cold Baltic seafloor. This specific resting geometry dictates exactly how the trapped pollutants interact with the surviving bunker systems. The observed fuel appears buoyant enough to rise once it escapes, but heavy fuel oil does not behave with perfect simplicity. Its movement depends on density, temperature, salinity, weathering, and whether it has mixed with sediment. Inside the listed wreck, any remaining oil may migrate through internal voids and collect against higher surfaces where the hull geometry allows it, placing slow pressure on weakened seams and openings. This internal dynamic introduces the rigid physics of main hull containment limits. The thick bunker plating serves as the absolute physical barrier between a slow, controlled micro-leak and a catastrophic structural spill. The degradation of this century-old naval steel is never uniform across the length of the vessel. Galvanic corrosion attacks specific rivet lines, plate joints, and degraded seams at highly variable rates. This process slowly carves microscopic fissures directly through the solid hull. Driven by continuous upward buoyancy, the heavy oil forcefully navigates these tiny, fractured pathways. At one drop every 15 seconds, the leak shows that the primary steel envelope has not collapsed, but the containment barrier is failing at the millimeter scale. Recording the slow leak gives the engineering teams one narrow but important evidence gain. Fuel remains associated with the wreck, and the current release is gradual rather than a massive, uncontrolled plume. It also leaves the internal bunker system unresolved. Unseen collapse may have occurred inside the hull, allowing fuel to migrate through engineering spaces, separated lower tanks, and deteriorating bulkheads. That uncertainty drives the risk assessment. If the internal bulkheads have rusted away, the remaining payload could be pressing against a single degraded outer plate. If the cellular structure survives, the oil may still be compartmentalized across multiple tanks. The surviving main hull is slowly bleeding, but the staggering explosive violence that spared these aft bunkers is documented entirely elsewhere on the seabed. The next measurable clue is geometric. Approximately 20 meters of the bow section is missing from the main hull, forcing the investigation into the surrounding debris field. The damage pattern supports a narrower conclusion. Sonar imagery is consistent with a mine strike concentrated near the bow, with the surviving main hull still recognizable on its starboard side. The public survey record does not establish a seabed crater, a precise blast radius, or a complete mathematical timeline of structural failure. However, any forensic debris analysis is bounded by a serious safety concern. The wider area west of Saaremaa is known for shipwrecks and unexploded ordnance from more than one conflict, and any modern survey must assess that hazard before intrusive work begins. Corroded ammunition or mine-related debris may remain in or near the wreck area, but the public record does not prove an exact concentration of live warheads around a crater. The correct operational posture is caution. Teams must maintain safe standoff, identify hazards remotely where possible, and avoid intrusive sampling until the ordnance risk has been assessed by qualified specialists. The physics of the sinking are fully documented, leaving authorities to decide the final fate of the wreck. Marine engineers face a razor-thin trade-off between proactively remediating an environmental threat and destabilizing the containment system holding it back. Across the global seafloor, at least 8,500 potentially polluting wrecks present some version of this dilemma. Extraction may permanently remove the hazard, but it can also turn a controlled risk into an uncontrolled release. Faced with those boundaries, the United Kingdom Ministry of Defence Salvage and Maritime Operations Team has treated Cassandra as a survey-led risk assessment case rather than a simple recovery job. Intrusive pumping remains a conditional option dependent on evidence, authorization, heel condition, and whether intervention becomes safer than continued monitoring. That posture turns the wreck into a practical reference case for wider maritime risk management. Instead of treating every sunken military vessel as an immediate recovery job, authorities can use repeated, non-intrusive surveys to classify, compare, and triage hazardous wrecks across multiple seasons. The value lies in a monitored baseline. The threat is not dismissed but measured, revisited, and updated as new data arrives. This strategic monitoring approach delivers a profound positive knowledge gain. The engineering team successfully established a comprehensive non-intrusive risk characterization blueprint that completely respects the sovereign immunity and absolute legal boundaries of the maritime grave. They proved it is entirely possible to heavily monitor a massive, degrading warship, log its hazard profile, and map its overarching environmental threat without ever touching the steel plating or desecrating the human remains trapped inside the hull. However, this disciplined operational restraint is fundamentally restricted by an unyielding proof ceiling. While the marine engineers can calculate the overall rate of galvanic corrosion and mathematically track the slow loss of structural integrity, the exact time frame for total structural collapse simply cannot be definitively proven. The precise moment when the overarching steel geometry will finally fail remains completely theoretical. Mathematical degradation modeling is incredibly sophisticated, but it cannot perfectly predict when a specific degraded bulkhead will instantly buckle under extreme deep water pressure. The continuous decay of the maritime steel is an absolute physical certainty, but the exact date of final structural failure cannot be known. The site remains locked in a permanent state of mathematical calculation, where catastrophic failure is a guaranteed event with an entirely unknown arrival time. The non-intrusive survey work achieved a vital first objective. It located and imaged the wreck, creating an external baseline for future assessment. Later risk work must still determine how much oil and other pollutants remain on board, what condition the hull is in, and whether any intervention can be justified. The operation demonstrated engineering restraint under extreme environmental pressure. The deep water wreckage may remain untouched unless the evidence shows that action is necessary, legal, and safer than continued monitoring. For now, the warship remains in the darkness as survey teams build the knowledge needed to decide whether observation is enough or whether the slow failure of the heavy steel hull will eventually demand intervention.